10.6 Alternating Series and Conditional Convergence. The outline of this video is as follows. We will begin by defining what an alternating series is and learning a simple, three-part test to determine if it converges. Next, we will see how to estimate the sum of a convergent alternating series, which is a very practical tool. After that, we will introduce the critical distinction between absolute and conditional convergence. This will lead us to our final topic, the surprising and important consequences of rearranging the terms of a series, where we will find that the order of addition can sometimes change the sum. Now we will turn our attention to a special type of series called an alternating series, where the signs of the terms switch back and forth. An alternating series is one in which the terms are alternately positive and negative. This means the general term a sub n can be written as the quantity -1 to the power of n plus 1 times a positive number, u sub n. The term u sub n simply represents the positive magnitude or absolute value of each term in the series. Let us look at three key examples. First is the alternating harmonic series, which is 1 minus 1/2 plus 1/3, and so on. As we will soon prove, this series converges. The second example is an alternating geometric series, where the ratio is -1/2. Since the absolute value of this ratio is less than 1, we already know it converges. Finally, the series 1 minus 2 plus 3 minus 4 diverges. This is because its terms grow in magnitude and do not approach 0, which is a fundamental requirement for any series to converge. The key takeaway is that the alternating sign pattern is a defining feature, but it does not by itself guarantee convergence. Here we have the formal statement of the alternating series test, which gives us a straightforward way to check for the convergence of many alternating series. For a series of the form u sub 1 minus, u sub 2 plus, u sub 3, and so on to converge, it must satisfy all three of the following conditions. First, the terms u sub n, which represent the positive magnitudes, must all be positive. Second, this sequence of positive terms must eventually become non-increasing. This means that each term is greater than or equal to the next term for all terms beyond a certain point in the series. Third, the limit of these terms, u sub n as n approaches infinity, must be 0. The terms must shrink all the way to 0. A critical point is that this test can only be used to prove convergence. If a condition is not met, the test is inconclusive. The only exception is if the limit of the terms is not 0. In that case, the series diverges by the nth term test. In short, if the positive terms of an alternating series eventually decrease towards 0, the series converges. Let us apply the alternating series test to see how to use its three conditions. Our first example is the classic alternating harmonic series. Here the terms u, n, which are 1 over n, are always positive. The sequence is also non-increasing, since 1 over n is always greater than or equal to 1 over the quantity n plus 1. Finally, the limit of 1 over n as n approaches infinity is 0. Since all three conditions are met, the series converges. For our second example, verifying the non-increasing condition is less obvious. A powerful technique is to define a continuous function, f of x, that matches our sequence terms, u, n. If the derivative of this function is negative, or 0 for x beyond some value, then the sequence is non-increasing from that point onward. For the sequence u, n equals 10n over the quantity n squared plus 16, we can see that its associated derivative is negative whenever x is greater than or equal to 4. This proves the sequence is non-increasing for n greater than or equal to 4, satisfying the condition. Using the derivative is a reliable way to check the non-increasing condition when it is not immediately clear. Let us visualize how a convergent alternating series approaches its limit. This graphical view provides a strong intuition for why the alternating series test works. Imagine the partial sums as points on a number line. We start at the origin and take a step forward by the amount, u1, landing at the first partial sum, s1. To find the second partial sum, s2, we subtract u2, which means we take a step backward. Then, to get s3, we add u3, taking a step forward again. We continue this back and forth, or seesaw motion. Because the series satisfies the test's conditions, each step is smaller than the one before it, and the step sizes eventually shrink to zero. This causes the partial sums to oscillate with decreasing amplitude, homing in on a single value. The key takeaway is that the true sum of the series, L, is always trapped between any two consecutive partial sums. Now that we know how to test if an alternating series converges, we can ask how to estimate its sum. The alternating series estimation theorem provides a powerful and simple way to determine the accuracy of our approximation. This theorem applies to any series that satisfies the alternating series test. It states that if you approximate the total sum, L, using a partial sum of n terms, called S sub n, the error is remarkably easy to bound. The absolute value of the error, which is the difference between the true sum L and your partial sum S sub n, is always less than the absolute value of the very next term in the series, u sub n plus 1. This is often called the first unused term. For example, if you sum the first 10 terms, your error is smaller than the magnitude of the 11th term. The theorem also tells us that the true sum L is always trapped between any two consecutive partial sums, and that the error has the same sign as the first unused term. This tells you whether your approximation is an overestimate or an underestimate. The essential result is that for a convergent alternating series, the first neglected term tells you the maximum possible error. Let us apply the alternating series estimation theorem to an example where we know the exact sum, so we can directly check the theorem's validity. We will consider the alternating geometric series whose sum is exactly 2/3. First, we approximate this sum by calculating the partial sum of the first 8 terms, which we call S sub 8. This value is approximately 0.664. According to the estimation theorem, the absolute error of this approximation should be less than the magnitude of the first term we left out. The first unused term is the 9th term, which has a value of 1 over 256, or about 0.0039. This is the theorem's predicted upper bound for our error. Now we can calculate the actual error by subtracting our approximation from the true sum of 2/3. The result is about 0.0026. Comparing the two, we see that the actual error is indeed less than the predicted error bound. The theorem works perfectly, giving us a guaranteed upper limit on the error of our partial sum approximation. We can now formalize the two distinct ways that a series with negative terms can converge, which we call absolute and conditional convergence. First, a series is said to converge absolutely if the corresponding series formed by taking the absolute value of every term also converges. In simple terms, if making all the terms positive does not stop the series from converging, it is absolutely convergent. Second, a series converges conditionally if the original series converges, but the series of its absolute values diverges. Its convergence is therefore conditional upon the cancellation that the negative terms provide. The alternating harmonic series is our classic example of a conditionally convergent series. This leads to a crucial one-way relationship. If a series converges absolutely, then it is guaranteed to converge. However, The reverse is not necessarily true, as a series can converge without converging absolutely. The essential difference is whether a series relies on its negative terms to converge. Let us explore an important example that introduces a new classification for convergent series. We will focus on the alternating harmonic series, which is the sum from n equals 1 to infinity of the quantity -1 to the power of n plus 1, all divided by n. From our work with the alternating series test, we have already established that this series converges. Now we ask a new question. Does the series formed by the absolute values of its terms also converge? Taking the absolute value of each term simply removes the alternating sign, leaving us with the sum of 1 over n. This is the standard harmonic series, which we know diverges. This situation, where an alternating series converges, but its corresponding series of absolute values diverges, is very significant. We define this behavior as conditional convergence. Therefore, the alternating harmonic series is the classic example of a conditionally convergent series. Let us examine an important class of alternating series called the alternating P series, where the type of convergence is determined by the value of the exponent, p. The series is the sum of -1 to the power of n minus 1, all divided by n to the power of p. For any positive p, the terms decrease in magnitude and approach 0, so the series always converges by the alternating series test. Now we ask, is the convergence absolute or conditional? To find out, we look at the series of absolute values, which is simply the sum of 1 over n to the power of p. We recognize this as a standard p series. We know from our earlier work that a p series converges only when p is strictly greater than 1. Therefore, the alternating p series converges absolutely when p is greater than 1. If p is greater than 0 and less than or equal to 1, the p series of absolute values diverges. Since the original alternating series converges, while its absolute series diverges, it converges conditionally in this range. The key result is that the alternating p series converges absolutely for p greater than 1 and conditionally for p between 0 and 1. This slide presents a crucial theorem about rearranging the terms of an infinite series, which highlights a major difference between absolute and conditional convergence. The rearrangement theorem tells us that for any absolutely convergent series, you can reorder the terms in any way you like. The new, rearranged series will still converge absolutely, and, most importantly, it will have the exact same sum as the original series. This is the behavior we expect from adding a finite number of terms. However, the warning here is critical. This guarantee completely breaks down for conditionally convergent series. If a series converges, but not absolutely, then rearranging its terms can change the sum. In fact, you can reorder the terms of a conditionally convergent series to make the new sum equal any real number you can think of, or even make the series diverge. The essential result is that for absolutely convergent series, the order of summation does not matter, but for conditionally convergent series, the order is a fixed part of the series. Definition. Finally, our summary covers a special case: series whose terms alternate in sign. For these alternating series, we have a dedicated tool called the alternating series test. This test provides a straightforward path to check for convergence if 3 specific conditions are met. First, the absolute values of the terms must all be positive. Second, these terms must be non-increasing, meaning each term is less than or equal to the one before it, at least eventually. Third, the limit of the terms must go to 0. A classic example is the alternating harmonic series, which converges because it satisfies all three of these rules. It is important to remember that this test can only be used to prove convergence. If a series fails the test, you cannot conclude that it diverges. You must use another method, such as the nth term test. In summary, for a series with strictly alternating signs, the alternating series test is the primary tool to determine convergence. Let us summarize the key ideas we have discussed about alternating series. We started by defining them as series whose terms alternate in sign. We then introduced the alternating series test, which provides three simple conditions for convergence. The terms must be positive, non-increasing, and approach zero. A powerful consequence is the estimation theorem. This theorem states that when you approximate the sum with a partial sum, your error is less than the absolute value of the first term you omit, giving us a practical error bound. We also distinguished between two kinds of convergence. A series converges absolutely if the series of its absolute values converges. If not, but the original series still converges, we call it conditional convergence. This difference is critical because absolutely convergent series can be rearranged without changing their sum, a property that conditionally convergent series do not have. To wrap up our discussion, let us look at a few questions that bring together the key concepts we have covered. These problems are designed to test your understanding of convergence and error estimation for alternating series. The first question asks you to determine if a given series converges absolutely or conditionally. You are told that it converges by the alternating series test, so your job is to analyze the series of the absolute values. Think about which test you would use for the series whose terms are the quantity n plus 1 divided by the quantity n squared plus 1. The second question is more conceptual. It asks why the alternating series estimation theorem is such a powerful tool. Its real value is that it gives us a simple way to find a very good approximation for a series' sum, along with a guaranteed error bound, which is crucial in practical applications. Finally, the third question is a direct application of that theorem. To approximate the sum with an error less than 1/1000th, you need to find how many terms are required. Remember, the error is no larger than the magnitude of the first term you leave out.